ladies and gentlemen, esteemed colleagues, and curious minds. Today, I stand before you to unravel the intricate tapestry woven by the marvels of electricity, a fundamental force that powers our modern world. Electricity is not just a mere convenience, it is the lifeblood of our civilization, driving everything from our homes and industries to our advanced technologies and cutting-edge innovations. Let us embark on a journey through the realms of engineering and physics to understand the principles, mechanisms, and wonders that make electricity the cornerstone of our existence. At its core, electricity is the movement of electric charge, a concept deeply rooted in the principles of physics. The story begins with the atom, the basic unit of matter. Within the atom, electrons, which are negatively charged particles, orbit the nucleus composed of positively charged protons and neutral neutrons. The flow of electrons from one atom to another constitutes an electric current, which is the essence of electricity. The behavior of electrons and the phenomena of electricity are governed by electromagnetic forces, one of the four fundamental forces of nature. James Clerk Maxwell, a pioneering physicist, formulated the set of equations that describe how electric and magnetic fields interact, known as Maxwell's equations. These equations reveal that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field, paving the way for the generation and transmission of electric power. The generation of electricity involves converting various forms of energy into electrical energy. This process predominantly occurs in power plants, where mechanical energy is transformed into electrical energy using generators. The principle behind this conversion is electromagnetic induction, discovered by Michael Faraday in the 1830s. Faraday's law of electromagnetic induction states that a change in magnetic flux through a circuit induces an electromotive force, EMF, in the circuit. In a generator, this principle is harnessed by rotating a coil of wire within a magnetic field, or by rotating a magnetic field around a stationary coil. The mechanical energy required for this rotation can come from various sources, such as steam turbines, water turbines, wind turbines, or internal combustion engines. This transformation of energy is a testament to the versatility and adaptability of engineering solutions to harness natural forces for human benefit. The field of electrical engineering is dedicated to harnessing, distributing, and utilizing electrical energy efficiently and safely. Electrical engineers design and maintain the infrastructure that delivers electricity from power plants to end users, ensuring that the power is stable, reliable, and meets the required standards. One of the primary challenges in electrical engineering is the transmission of electricity over long distances. This is achieved through high-voltage power lines, which minimize energy losses due to resistance. Transformers play a crucial role in this process by stepping up the voltage for transmission and stepping it down for safe usage in homes and businesses. The power grid, a vast network of interconnected power lines and substations, ensures that electricity is distributed evenly and can be rerouted in case of faults or maintenance. The complexity and sophistication of this grid highlight the intricate planning and precision engineering required to keep our world powered. From the simplest light bulb to the most complex computer, a myriad of devices utilize electricity to perform their functions. The functioning of these devices relies on various electrical and electronic components, each governed by principles of physics and engineering. Basic components like resistors, capacitors, and inductors manipulate electrical currents in circuits. Resistors impede the flow of electric current, capacitors store and release electrical energy, and inductors resist changes in current. Together, they form the building blocks of more complex electronic circuits. The advent of semiconductors revolutionized the field of electronics. Semiconductors, materials with conductivity between conductors and insulators, form the basis of modern electronic devices. Transistors, made from semiconductor materials, act as switches or amplifiers, and are integral to the operation of computers, smartphones, and countless other devices. The invention of the transistor marked the beginning of the digital age, enabling the development of integrated circuits and microprocessors. This technological leap underscores the synergy between physics and engineering, where understanding atomic-level interactions can lead to macroscopic technological advancements. As we look to the future, the sustainable generation of electricity becomes paramount. Renewable energy sources, such as solar, wind, and hydroelectric power, offer promising alternatives to fossil fuels, reducing our carbon footprint and mitigating climate change. Solar power harnesses energy from the sun using photovoltaic cells, which convert sunlight directly into electricity. The physics behind this involves the photoelectric effect, where photons striking a material release electrons, creating an electric current. Advances in solar technology and materials science continue to improve the efficiency and affordability of solar panels. Wind turbines convert the kinetic energy of wind into mechanical energy, which is then transformed into electrical energy by generators. The aerodynamic design of turbine blades and advancements in materials engineering have significantly increased the efficiency and capacity of wind power installations. These innovations in renewable energy highlight the ongoing evolution of engineering solutions to meet the growing demand for clean and sustainable energy sources. The journey of electricity from fundamental physics to practical engineering applications is a testament to human ingenuity and our quest for understanding and harnessing the forces of nature. Electricity has transformed our world, driving technological progress and shaping our daily lives. As we continue to innovate and embrace renewable energy sources, the future of electricity promises to be brighter, more sustainable, and ever more integral to our society. Thank you for joining me on this exploration of the wonders of electricity. May we continue to push the boundaries of knowledge and engineering to power a brighter future for all. At its core, electricity is the movement of electric charge, a concept deeply rooted in the principles of physics. The story begins with the atom, the basic unit of matter. Within the atom, electrons, which are negatively charged particles, orbit the nucleus composed of positively charged protons and neutral neutrons. The flow of electrons from one atom to another constitutes an electric current, which is the essence of electricity. The behavior of electrons and the phenomena of electricity are governed by electromagnetic forces, one of the four fundamental forces of nature. James Clerk Maxwell, a pioneering physicist, formulated the set of equations that describe how electric and magnetic fields interact, known as Maxwell's equations. These equations reveal that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field, paving the way for the generation and transmission of electric power. Delving deeper into the nature of electric charge, we find that it is a fundamental property of matter. Charges can be positive or negative, and the interaction between these charges is described by Coulomb's law, which states that the force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This electrostatic force is what holds atoms and molecules together, and it is also the basis for the operation of capacitors, which store electrical energy by maintaining a separation of charge. Capacitors are essential components in many electronic circuits, providing functions such as energy storage, power conditioning, signal coupling or decoupling, and filtering. The concept of electric current is intimately connected with Ohm's law, which relates the current flowing through a conductor to the voltage across it and the resistance of the conductor. This relationship is fundamental to understanding how electrical circuits function. Resistance, a measure of how much a material opposes the flow of electric current, is determined by the material's properties and its temperature. Materials with low resistance, such as metals, are good conductors of electricity, while materials with high resistance, such as rubber or glass, are insulators. The engineering challenge often lies in optimizing the materials and design of circuits to minimize unwanted resistance and manage heat dissipation. ensuring efficient operation and longevity of electronic devices. Electromagnetic induction, a phenomenon discovered by Michael Faraday, is the principle behind electric generators and transformers. Faraday's experiments demonstrated that a changing magnetic field could induce an electric current in a conductor. This discovery is the cornerstone of how we generate electricity today. In a generator, mechanical energy, often derived from steam turbines, water turbines, or wind turbines, is used to rotate a coil within a magnetic field, thereby inducing an electric current. Transformers, on the other hand, use electromagnetic induction to transfer electrical energy between two or more coils of wire, which allows the voltage to be increased or decreased. This ability to adjust voltage levels is crucial for efficient power transmission over long distances, reducing energy losses that occur due to resistance in the wires. In the realm of semiconductor physics, the behavior of electrons in materials that are neither good conductors nor good insulators opens up a world of possibilities. Semiconductors, such as silicon, have electrical properties that can be precisely controlled by adding impurities, a process known as doping. This ability to control electrical properties has led to the development of diodes, transistors, and integrated circuits, which are the building blocks of all modern electronic devices. Transistors, for instance, can amplify electrical signals or act as switches that turn current on and off, and they are fundamental to the operation of computers, enabling binary processing and data storage. As we transition to renewable energy sources, understanding the physics and engineering behind electricity generation becomes even more critical. Photovoltaic cells, which convert sunlight directly into electricity, rely on the photoelectric effect, where photons striking a semiconductor material release electrons, creating a flow of current. Wind turbines convert the kinetic energy of wind into mechanical energy, which is then transformed into electrical energy by generators. The efficiency of these systems depends on advanced materials and innovative engineering designs that maximize energy capture and conversion while minimizing losses. The integration of renewable energy into the power grid also presents challenges in terms of storage and distribution, requiring sophisticated engineering solutions to ensure a reliable and stable supply of electricity. The continuous advancement in the fields of physics and electrical engineering propels us toward a future where electricity is generated, transmitted, and utilized with unprecedented efficiency and minimal environmental impact. Innovations in superconductivity, for example, promise to revolutionize power transmission by eliminating resistive losses. Superconductors are materials that can conduct electricity without resistance below a certain temperature, leading to the development of ultra-efficient power lines and advanced magnetic levitation technologies for transportation. Similarly, the development of smart grids, which use digital technology to monitor and manage the flow of electricity, aims to enhance the reliability, efficiency, and sustainability of our power systems, adapting to fluctuations in demand and integrating diverse energy sources seamlessly. The journey of electricity from fundamental physics to practical engineering applications is a testament to human ingenuity and our quest for understanding and harnessing the forces of nature. Electricity has transformed our world, driving technological progress and shaping our daily lives. As we continue to innovate and embrace renewable energy sources, the future of electricity promises to be brighter, more sustainable, and ever more integral to our society. Thank you for joining me on this exploration of the wonders of electricity. May we continue to push the boundaries of knowledge and engineering to power a brighter future for all. The generation of electricity involves converting various forms of energy into electrical energy, a process that predominantly occurs in power plants where mechanical energy is transformed into electrical energy using generators. This conversion process hinges on the principle of electromagnetic induction, discovered by Michael Faraday in the 1830s. Faraday's groundbreaking work revealed that a change in magnetic flux through a circuit induces an electromotive force, EMF, in that circuit, which forms the basis for how generators function. In a generator, this principle is harnessed by rotating a coil of wire within a magnetic field or by rotating a magnetic field around a stationary coil. This rotation alters the magnetic flux through the coil, thereby inducing an EMF and generating electric current. The mechanical energy required for the rotation of the generator's components can be derived from various sources, each tapping into different forms of energy. Steam turbines are one of the most common sources, especially in thermal power plants. These turbines operate by heating water in a boiler to produce steam, which then expands and spins the turbine connected to the generator. The heat energy required to produce steam can come from burning fossil fuels such as coal, natural gas, or oil, or from nuclear reactions in nuclear power plants. In nuclear reactors, the fission of uranium or plutonium atoms generates a tremendous amount of heat, which is used to convert water into steam. Water turbines, commonly used in hydroelectric power plants, rely on the potential energy of water stored at a height. This water is released to flow down through turbines, converting its potential energy into mechanical energy that spins the turbines. The engineering marvel of hydroelectric power lies in its ability to produce large amounts of electricity without burning fuels, thereby significantly reducing carbon emissions. The design and construction of dams and reservoirs for hydroelectric power require extensive knowledge of civil engineering and environmental science to manage water resources sustainably and minimize ecological impacts. Wind turbines, another source of mechanical energy, convert the kinetic energy of wind into electrical energy. The aerodynamic design of the blades ensures that they capture as much wind energy as possible. As the wind blows, it causes the blades to rotate, driving the generator to produce electricity. The engineering behind wind turbines involves advanced materials science to create lightweight yet strong blades, as well as sophisticated control systems to optimize blade pitch and rotor speed for varying wind conditions. Moreover, the placement of wind turbines requires careful consideration of meteorological data to maximize energy capture and efficiency. Internal combustion engines are also used in some power plants, particularly in smaller or more remote installations where other forms of energy might not be readily available. These engines burn fuel to produce mechanical energy, which then drives a generator. While internal combustion engines are versatile and can run on various fuels, including gasoline, diesel, and biofuels, they are typically less efficient than steam turbines and produce more emissions. However, they remain a valuable part of the energy mix, especially for backup power and in locations where other infrastructure is not feasible. Each method of generating electricity has its own set of engineering challenges and innovations. For instance, managing the heat produced in thermal power plants involves complex cooling systems to prevent overheating and ensure efficient operation. In nuclear power plants, ensuring the safety and containment of radioactive materials is paramount, involving advanced reactor designs, robust safety protocols, and extensive monitoring systems. The development and deployment of renewable energy sources like wind and hydroelectric power require an interdisciplinary approach, combining environmental science, materials engineering, and advanced computer modeling to optimize performance and integration into the power grid. The generation of electricity is a complex interplay of physics and engineering, transforming various forms of mechanical energy into electrical energy through the principles of electromagnetic induction. This process is foundational to our modern society, powering homes, industries, and technologies. As we advance, the continued refinement of these technologies and the integration of sustainable energy sources will be crucial in meeting the growing global energy demands while minimizing environmental impacts. The field of electrical engineering is dedicated to harnessing, distributing, and utilizing electrical energy efficiently and safely. Electrical engineers are responsible for designing and maintaining the complex infrastructure that delivers electricity from power plants to end users. This infrastructure must ensure that the power remains stable, reliable, and meets the stringent standards required for both domestic and industrial use. A key aspect of this field is the meticulous planning and execution of electrical systems to prevent outages, manage load distributions, and optimize the overall performance of the grid. Engineers must consider factors such as voltage levels, current flow, and the materials used in constructing transmission lines to maximize efficiency and safety. One of the primary challenges in electrical engineering is the transmission of electricity over long distances. When electricity is transmitted over vast stretches, it encounters resistance in the wires, leading to energy losses in the form of heat. To minimize these losses, electrical engineers employ high-voltage power lines, as increasing the voltage decreases the current for a given power level, thereby reducing resistive losses according to Joule's law. P equals I squared R. This principle underscores the necessity of high-voltage transmission for efficient long-distance power delivery. Engineers must carefully design these high-voltage systems, taking into account the potential for electrical arcing, insulation requirements, and the environmental impact of overhead and underground power lines. Transformers play a crucial role in this process by stepping up the voltage for transmission and stepping it down for safe usage in homes and businesses. The operation of transformers is based on the principles of electromagnetic induction, discovered by Faraday. When an alternating current flows through the primary coil of a transformer, it creates a changing magnetic field, which induces a current in the secondary coil. By adjusting the number of turns in the primary and secondary coils, engineers can control the voltage levels. This capability is essential for matching the high voltages required for efficient transmission with the lower, safer voltages needed for consumer use. Transformers are strategically placed throughout the power grid to manage voltage levels and ensure efficient energy distribution. The power grid itself is a marvel of engineering, a vast network of interconnected power lines and substations designed to ensure that electricity is distributed evenly and can be rerouted in case of faults or maintenance. Engineers must design the grid to handle varying loads, prevent bottlenecks, and integrate diverse power sources, including renewable energy. Modern grids often employ smart grid technology, which uses advanced sensors, communication networks, and automation to monitor and manage the flow of electricity in real time. This technology allows for greater flexibility, efficiency, and resilience, enabling the grid to respond dynamically to changes in demand and supply, integrate renewable energy sources, and recover more quickly from disruptions. In the realm of distribution, the challenge is to deliver electricity to consumers in a manner that is both efficient and reliable. Electrical engineers design distribution networks that extend from substations to end users, ensuring that each home and business receives a steady supply of power. This involves meticulous planning of distribution routes, the installation of protective devices such as circuit breakers and fuses, and the implementation of control systems to monitor and manage the flow of electricity. Engineers also work on improving the infrastructure to minimize losses, enhance reliability, and accommodate future growth in demand. This includes upgrading older systems, integrating new technologies, and ensuring compliance with safety standards and regulations. Electrical engineering also encompasses the development and implementation of technologies to optimize energy usage and improve sustainability. Engineers design energy-efficient devices and systems, develop renewable energy technologies, and work on smart grid initiatives to enhance the overall efficiency of the power grid. They also focus on energy storage solutions, such as batteries and supercapacitors, which are crucial for balancing supply and demand, particularly with the increasing penetration of intermittent renewable energy sources like solar and wind. By improving energy storage capabilities, engineers help to stabilize the grid, reduce the need for fossil fuel-based peaking power plants, and enhance the overall sustainability of the energy system. Electrical engineering is a dynamic and essential field dedicated to the efficient and safe harnessing, distribution, and utilization of electrical energy. The challenges are numerous and complex, requiring a deep understanding of both theoretical principles and practical applications. Through the continuous innovation and dedication of electrical engineers, we are able to enjoy the benefits of a reliable and sustainable power supply, powering our homes, industries, and the countless technologies that define modern life. As we look to the future, the role of electrical engineering will only become more critical in addressing the energy challenges of our time and driving progress towards a more sustainable and electrified world. From the simplest light bulb to the most complex computer, a myriad of devices utilize electricity to perform their functions. The functioning of these devices relies on various electrical and electronic components, each governed by principles of physics and engineering. Basic components like resistors, capacitors, and inductors manipulate electrical currents in circuits. Resistors, for instance, are designed to impede the flow of electric current by providing resistance, thereby controlling the current and voltage within a circuit. They are essential in protecting components from receiving too much current, which could cause overheating and damage. Capacitors, on the other hand, store and release electrical energy. When connected to a power source, they accumulate charge on their plates, creating a potential difference. When needed, they can discharge this energy rapidly, making them invaluable in applications requiring quick bursts of power, such as in flash photography or in the smoothing out of power supply fluctuations. Inductors are another fundamental component, crucial for their ability to resist changes in current. An inductor, typically a coil of wire, generates a magnetic field when current flows through it. This magnetic field stores energy and opposes any changes in the current, which is especially useful in filtering applications where stable current is necessary. Inductors are widely used in power supplies and transformers, where their properties help maintain consistent voltage levels and reduce electromagnetic interference. Together, resistors, capacitors, and inductors form the building blocks of more complex electronic circuits, working in harmony to manage and manipulate electrical signals for a wide range of applications. The advent of semiconductors revolutionized the field of electronics. Semiconductors, materials with conductivity between conductors and insulators, form the basis of modern electronic devices. Silicon, the most commonly used semiconductor material, has unique properties that allow it to control electrical current precisely. By introducing impurities into silicon, a process known as doping, engineers can create regions with excess electrons, N-type, or holes, P-type, which are crucial for the operation of semiconductor devices. The junctions between these regions form diodes and transistors, the latter being one of the most significant inventions in electronics. Transistors, made from semiconductor materials, act as switches or amplifiers, and are integral to the operation of computers, smartphones, and countless other devices. As switches, transistors can turn electrical signals on and off, enabling binary computing, which is the foundation of digital electronics. As amplifiers, they can increase the power of weak signals, making them vital in applications such as audio devices and radio transmission. The invention of the transistor marked the beginning of the digital age, enabling the development of integrated circuits and microprocessors. Integrated circuits, or ICs, are essentially miniaturized circuits containing millions of transistors packed into tiny chips. These chips have drastically increased the processing power and efficiency of electronic devices, leading to the rapid advancement of technology. Microprocessors, which are complex ICs containing the central processing unit, CPU, of a computer, have transformed every aspect of modern life. They are the brains of computers, executing instructions and performing calculations at incredible speeds. The continuous miniaturization of transistors, following Moore's law, has allowed for more powerful and efficient microprocessors, driving innovations in fields ranging from personal computing to artificial intelligence. This relentless progress in semiconductor technology has not only enhanced computational power but also reduced energy consumption, making devices more efficient and environmentally friendly. Moreover, advancements in materials science and nanotechnology are paving the way for the next generation of electronic components. Researchers are exploring new semiconductor materials, such as graphene, which promise even greater conductivity and flexibility than silicon. These innovations hold the potential to revolutionize fields like flexible electronics and quantum computing, where traditional silicon-based components are reaching their physical limits. In quantum computing, for example, quantum bits or qubits, which can exist in multiple states simultaneously, offer a dramatic increase in processing power for certain tasks, far beyond the capabilities of classical computers. The journey from basic electrical components to sophisticated microprocessors underscores the profound impact of engineering and physics on modern technology. Each innovation builds upon fundamental principles, pushing the boundaries of what is possible and driving the relentless march of progress. As we continue to explore new materials and technologies, the future of electronics promises to be even more remarkable, with breakthroughs that could transform our world in ways we can only imagine. As we look to the future, the sustainable generation of electricity becomes paramount. Renewable energy sources, such as solar, wind, and hydroelectric power, offer promising alternatives to fossil fuels, reducing our carbon footprint and mitigating climate change. Solar power harnesses energy from the sun using photovoltaic cells, which converts sunlight directly into electricity. The physics behind this involves the photoelectric effect, where photons striking a material release electrons, creating an electric current. Advances in solar technology and materials science continue to improve the efficiency and affordability of solar panels. Innovations in thin-film technology, for instance, have led to the development of flexible, lightweight solar cells that can be integrated into various surfaces, from rooftops to portable devices. Moreover, research into perovskite solar cells has shown great potential for higher efficiency rates and lower production costs, making solar energy more accessible and sustainable. Wind energy is another crucial player in the quest for renewable energy. Wind turbines convert the kinetic energy of wind into mechanical energy, which is then transformed into electrical energy by generators. The aerodynamic design of turbine blades, inspired by the wings of birds and the fins of marine animals, maximizes the capture of wind energy, allowing turbines to operate efficiently even at lower wind speeds. Advanced materials, such as carbon fiber composites, have been employed to construct lighter and stronger blades, enhancing their durability and performance. Additionally, the integration of smart sensors and control systems enables real-time monitoring and optimization of turbine operations, further increasing energy output and reliability. Offshore wind farms, which harness the stronger and more consistent winds over the ocean, represent a significant advancement in this field, offering substantial contributions to the renewable energy grid. Hydroelectric power, one of the oldest and most established forms of renewable energy, continues to evolve with modern engineering practices. By utilizing the potential energy of stored water in dams, hydroelectric plants generate electricity through the movement of water driving turbines. Innovations in turbine design, such as the use of adjustable blades and variable speed generators, have improved the efficiency and adaptability of hydroelectric systems to varying water flow conditions. Additionally, the development of small-scale and run-of-the-river hydroelectric systems provides sustainable energy solutions for remote and rural areas without the need for large dams, thus minimizing environmental impact. Beyond these traditional renewable sources, Emerging technologies like wave and tidal energy offer exciting possibilities for the future. Wave energy converters capture the energy from surface waves, while tidal energy harnesses the gravitational pull of the moon and sun on the Earth's oceans. These technologies, although still in the experimental stages, benefit from the predictability and consistency of ocean movements, providing a reliable and continuous source of energy. Engineering advancements in robust materials and efficient energy conversion mechanisms are critical to overcoming the challenges posed by the harsh marine environment. Energy storage technologies also play a pivotal role in the future of sustainable electricity generation. The intermittent nature of renewable energy sources necessitates efficient storage solutions to ensure a stable and reliable power supply. Battery technologies, such as lithium-ion and emerging solid-state batteries, have seen significant improvements in energy density, charging speed, and lifespan. These advancements are crucial for integrating renewable energy into the grid and enabling widespread adoption of electric vehicles. Furthermore, innovative approaches like pumped hydro storage, where excess electricity is used to pump water uphill to a reservoir, and then released to generate electricity when needed, offer large-scale energy storage solutions. Compressed air energy storage and flywheel energy storage are other promising technologies being explored to enhance the stability and resilience of the power grid. In conclusion, the engineering and physics behind the sustainable generation of electricity are driving us toward a future where renewable energy sources can meet our global energy demands. Continuous advancements in materials science, aerodynamics, fluid dynamics, and energy storage are essential to overcoming the challenges and maximizing the potential of these renewable technologies. As we innovate and improve these systems, we pave the way for a cleaner, more sustainable energy landscape that benefits both humanity and the planet. The journey is complex and demanding, but the rewards of a sustainable future powered by renewable energy are within our grasp. Let us continue to push the boundaries of science and engineering to achieve this vision. In conclusion, the journey of electricity represents a remarkable fusion of fundamental physics principles and ingenious engineering applications. It all begins with the intricate dance of electrons within the atom, where negatively charged particles orbit the positively charged nucleus, setting the stage for the phenomenon of electric charge. This fundamental aspect of nature, governed by electromagnetic forces, serves as the bedrock upon which our understanding of electricity is built. From the pioneering work of James Clerk Maxwell, who formulated the equations describing the interaction between electric and magnetic fields, to Michael Faraday's groundbreaking discoveries in electromagnetic induction, every step of the journey unveils the profound interconnectedness of physics and engineering. Electricity's transformative power is evident in every aspect of our modern world, from the illumination of our homes to the propulsion of our vehicles. It has fueled the engine of technological progress, propelling humanity into new frontiers of innovation and discovery. The advent of electricity paved the way for the Industrial Revolution, ushering in an era of unprecedented growth and prosperity. Today, it underpins the functioning of our interconnected global economy, enabling communication, transportation, healthcare, and countless other facets of modern life. Yet, as we marvel at the wonders wrought by electricity, we must also confront the pressing challenges posed by its consumption. The reliance on fossil fuels for electricity generation has exacted a heavy toll on our environment, contributing to pollution, climate change, and resource depletion. In response, the imperative to embrace renewable energy sources has never been more urgent. Solar, wind, hydroelectric, and other forms of renewable energy offer a path towards a more sustainable future, one in which the generation of electricity harmonizes with the natural rhythms of the planet. The pursuit of renewable energy technologies represents a formidable engineering endeavor, requiring ingenuity, innovation, and collaboration on a global scale. From the development of advanced photovoltaic materials to the design of efficient wind turbine systems, Engineers are at the forefront of this quest for sustainable energy solutions. Moreover, the integration of renewable energy sources into existing power grids poses technical challenges that demand sophisticated engineering solutions. Smart grid technologies, energy storage systems, and grid-scale infrastructure projects are just a few examples of the engineering innovations driving the transition towards a renewable energy future. As we stand on the threshold of a new era in the history of electricity, we are called upon to harness the full potential of human ingenuity and creativity. The challenges we face are immense, but so too are the opportunities for progress and innovation. By continuing to push the boundaries of knowledge and engineering, we can unlock new frontiers in energy generation, distribution, and consumption. Together, let us embark on this journey towards a brighter, more sustainable future powered by the wonders of electricity. Thank you for joining me on this exploration, and may we forge ahead with determination and purpose, inspired by the possibilities that lie ahead.